All right, guys, we'll just wait a few minutes and before we start, just to give others an opportunity to join in. All right, guys, I think it's good to let's get started. We want to look at the visual interpretation of the derivative today. Now, you will recall when we started introducing this, uh, we said the power of calculus is that it allows us, or at least affords us, to be able to calculate the gradient at a point. Okay, so I'm just going to set up a number of points of interest here, uh, and then yeah, that will be then yeah uh, the focus of our discussion. So I'd like you to note a few things that I've got a tangent there. I've got a tangent here. Maybe we should, or maybe I should draw this line like that. Okay. Okay, this is not necessarily a tangent. It's just a straight line that passes through here because I want to illustrate this concept. And then let's have another one there. Yeah. Okay, those are not tangents, but just a straight line. And this is the reason I'm putting up the straight lines, okay? I usually talk about the slope man. So pay attention to what I'm about to do here as well, so that you see how it tallies up, relates with this visual here. So the slope man says, if you've got a straight line with a positive gradient, surely that's increasing. A straight line with a negative gradient decreasing. A straight line which is just vertical has an undefined gradient, and a straight line which is just horizontal has gradient 0. Okay, so this is what I call the slope man. Very, very friendly guy who helps us to really answer good questions or difficult questions in calculus. And you will see what I mean. I'm going to illustrate that to you. Now, what I need us to understand at this point is that we've got 3 points of interest. One is literally giving us the increasing slope vibes. The other is giving us the decreasing, and the other is literally giving us the 0. Okay, so I'd like us to take note of that. So this is what I mean. Now you will remember we set the gradient, very important also to note, we set the gradient, which is m, is basically the same as, so if this is f of x, then it is the same as f prime x. Okay, now right here, I've got a point, let's call this point A, and right there, I've got a point, let's call that point B, and right there, I've got a point, let's call that point C. So it is important that we note that the gradient at point A is actually positive. So when we say something is positive, in mathematical notation, we just say it is greater than 0. So then, which means something that is negative is less than 0. So I need you to note then that here the gradient at B is 0. Finally, I also want you to note that the gradient at C is actually equal to 0. These are 3 important cases that you will often need to use, or you'll often need to be able to answer some conceptual questions as far as curve sketching is concerned. So what we can then say is that the function, which is in blue, by the way, based on the gradient, I want you to see the relationship between the gradient test, which is basically the straight line test, and the conceptual understanding when it comes to this visual, this graph that I've got here, okay? I want you to note that at point A, if I were to draw a straight line at point A, which is the green one here, that straight line has a positive gradient. And because of that, I will say, I will say the function f is increasing at x equals to a. A is a number. We don't know what the number is at the stage, but surely it's a negative number looking at the grade we have here. So it's very important to note that. It is also important to note that this statement here means f is decreasing at x equals to b. Now, what is interesting is what is going on at c. But what we will say is, we will keep it very simple at the stage. We will say, because the gradient is not changing, it's zero, it's constant. You see that, right? We will then say f is stationary. It's not increasing or decreasing, so it's stationary at x equals to c. So in other words, there is a stationary point right here. And I want you to note that this is actually very important, guys. I want you to note that this stationary point is not just a stationary point. Another special name for a stationary point is the turning point. So I need you to take note that these are actually stationary points. They are both stationary points, but obviously another name for that is turning points. So again, I hope you're noticing how we're playing with words here. Sometimes I will ask you to calculate or find stationary points, and then sometimes I'll ask you to find turning points. Just know that we are referring to one and the same thing. Okay, so it is very important to take note of that. All right. So stationary points. How do you find stationary points? I've actually given you a hint right here. To find the stationary points, it means then that we must make the gradient, the derivative equals to zero, then we solve for x. This tool is very important. It is even applicable for the parabola. You know, the parabola, the quadratic function. This is a very universal principle. So if I've got a quadratic function like this, I just want to show you how critical this is. Very nice basic thing. If I've got a parabola and it goes like this, I sketch it like that. Okay, not accurate, but yeah, you get what I mean. And I want to find the stationary point. Okay, I can use the fact that at the stationary point or the turning point, the gradient of this thing is zero. I can use that fact. And we will go through those examples. You will see actually that this tool is very powerful, and you are more than welcome to use it at grade 12 level. You can use your calculus to find turning points. So in addition to this, just as a summary, please, I want to warn you again, please note the increasing, decreasing. We do get questions like this a lot. They will ask you for which values of x is the function increasing, or for which values of x is the function decreasing. Those things will come in, and guess what? You will need this theory that I'm sharing to be able to answer those. So what I'm going to do now is that I'm going to sort of look at some examples that we can use actually to just make sure that we understand what I have just shared right now. So I'm going to bring up an example, and then we're going to work through that together. All right, so here's our first example. We are told the graph of f of x is equal to 2x cubed minus 3x squared minus 12 is shown alongside. Then we must find by calculation whether this graph is increasing or decreasing at the given x values, okay? The key thing, we must first find the gradient. And what is the gradient? It is f prime of x. In this case, that will give us 6x squared minus a 6x minus a 12. So now, to answer question A, I will substitute a -2, and I hope you have your calculators. It will be great to actually get your help there. So please help me out there. F of 0, the f prime of 0, this one I will get, it's a -12. F prime of -1, I'll probably do this one too. That will be a 6, but then I'm gonna add another 6. So that looks like a 0. And then f prime of 3. Remember, this is what f prime is. So I'm substituting here in the gradient. I want to find what is happening to the gradient then. F prime of 3, I'll wait for someone to work that out for me, as well as f prime of 2. Okay. Please, guys, talk to me what you have. What is f prime of -2? You have substituted a -2. Fantastic. Thank you there, Dineo. We're getting a 24. Did someone do f prime of 3 and then f prime of 2? It will be great to have that so that we can draw some conclusions. Okay. Yeah, f prime of 0, we have agreed it's -12. F prime of -1 is a 0. And then D, f prime of 3, it is also 24. Thank you so much, Bali. 24, excellent. Let's do the last one. What about f prime of 2? F prime of 2 is 0. Thank you so much. Thank you, guys. Thank you for your cooperation. Excellent stuff. Now, we want to know, is this thing increasing or decreasing? If it is not, what is happening? Let's recap what we just learned here. We have learned from this that there are 3 possibilities. If we substitute a value and we get a positive value, in other words, a value that is bigger than 0, then we're going to conclude that it is increasing. If we substitute a value and we get a negative number, we will conclude that it is decreasing. If we substitute and we get exactly 0, we will conclude that that particular x value is actually an x coordinate of the stationary point. In other words, it's an x coordinate of the turning point. So let's check that. Looking at this, we substituted x minus 2, we got 24, but 24 is what? Is bigger than 0, isn't it? So because 24 is bigger than 0, we will then say f is increasing at x equals to -2. As you can see, for the second one, when we substitute 0, we're getting a -12. So -12 is surely less than 0. So we will conclude f is decreasing at x equals to 0. Then we look at -1. We got a 0, that one. So we will actually say f has a stationary point at x equals to 1. And if you want to know, sorry, not 1, but -1. And if you want to know the y coordinate of that stationary point, you can actually substitute -1 into the original, this one here now, into the original. Then that will give you the y coordinate of that stationary point. And if we roughly look at our graph here, surely there's the stationary point that we are talking about, because that is where -1 will be likely placed. As you can see, for the second stationary point, we actually have a positive value. And it looks like that positive value is actually 2, because that is what we get at E. F has a stationary point at x equals to 2. It seems that's what we are getting. Now, F at 3, what is happening? Well, 24 is bigger than 0, so F is increasing. In other words, it must point upwards, right? It must go in an upward direction. F is increasing at x equals to 3. So that's very important, right? Another little trick that I would like to advise, for example, let's say you did not have the sketch, but you got to know, and I just want to comment very briefly, but very important, on C and E here, on these two values. Okay, we have established that x equals to -1 and x equals to 2 are stationary points. Well, there is a stationary point there, a point at each of those. Now, you need to know whether your stationary point is what we call a local maximum or a local minimum. Let's talk about this. This here is a local max, and this one here is a local min. It's what we call a local minimum. And why? Obviously, this one stationary point is above this one here. So that's why that one is a local max and this one is a local min. It is not an absolute maximum because this graph continues on and on. And this one, that's why it's not an absolute minimum, because there are points below it. Same thing there. There are points above that. So that's why we can't say it is the absolute maximum of this graph. It's just a local maximum, all right? So it exists in a certain period or at a certain point in the domain. Now, whenever you want to know whether your stationary point is a local maximum or a local minimum, you can do a simple gradient test. In other words, this is what you can do. You can substitute a value that is less than -1. So in this case, for example, -2. -2, which we substituted in point A, gave us a +24. So we established that the gradient is positive there. What is interesting is that when we substituted a 0, we got a negative, and this is right there. We got a negative. So I want you to notice that this is what is happening. This is what is happening on your number line. So at -1, we know we've got a stationary point. There is a point. But I want to know, is this point a local maximum or not? Then guess what happens? When we do the gradient test by substituting a point that is before -1, or sorry, a value that is before -1, we got a positive. And when we substituted a value after the -1, we got a negative. This has to suggest to you a set face like that. And once that is the case, surely if you think of the parabola, that simplifies, or that rather displays a maximum situation. And you will notice, if we look at 2, if we look at the stationary point 2, and I want to know whether 2 is a local maximum or a local minimum, then I can substitute again a value before 2 and a value after 2. Let's take 1. I can guarantee you that if you substitute a 1, you will get a negative, so which means we are going in that direction. And then if you substitute any value after 2, which is 3, you will get that, which means then you are in this situation at the point 2. You're actually having a concave up shape. And so we will conclude that the stationary point at 2, or at x equals to 2, is actually a local minimum. So the change in signs, when you substitute a value before and after a stationary point, and the signs change, you're changing from positive to negative, then you know you are dealing with a maximum. If you change from a negative to a positive, then you will know that you are dealing with a minimum. We will keep talking about this. I'm introducing it. I'm just throwing some little stuff there and there. You will see as we sketch, I will come back to this. I will keep on emphasizing this to say, now think about the type of your stationary point. Is it a local minimum or is it a local maximum? What we are doing today really is to build up a foundation for a curve sketching, which we should be able to do in the next lesson. So it is very key that we are aware of these little things. Now, another one that we will maybe do is this. Let's take this example. So I've got a sketch that shows the graph of f of x is equal to negative x cubed plus 6x squared minus 9x plus 3. We want to calculate the coordinates of the stationary points. Now, what do we know about the coordinates of the stationary point? Well, we know that to find the stationary points, we must find the first derivative and make it equal to 0. And then we solve for x. Now, what is the first derivative? Well, the first derivative is negative 3x squared plus 12x minus 9. So we equate this to 0. It's going to be a nice quadratic. I'm going to divide by negative 3 all through, every term. So this will be minus 4x, and this will be a plus 3. And so we're going to factorize. Very nice basic factorization here. Otherwise, you are welcome to use your quadratic formula. Now, this would mean then x is a 3 or x is equal to a 1. So you see, it's just that here you have a sketch already. So you know this is 1 and you know this here is a 3 already. So you know 1 is your local mean and then 3 is a local max. So again, I want you to pay attention to this issue here of concavity. This region here is the situation. This is where we say the graph is actually concave up. And here we will say it is concave down. So I'm just going to throw these little things. When we do curve sketching, it will all come together. All right. So this is quite important to take note of. All right. Then question B will ask, when is the graph increasing and when is the graph decreasing? You don't really have to think a lot about this. You see, in this case, they are not asking for specific values. And I want you to see how the gradient test comes into play. So first of all, let us note that at 1 and 3, we are stationary, right? We're going to note that, right? Then I want you to note then that from -1 to the left, not -1, from 1 to the left, surely this is a downward slope. So which means the graph is decreasing there. On the other hand, if I look at the region between 1 and 3, when I look at the region between 1 and 3, surely I've got an upward slope there. So the graph is actually increasing in that region. And finally, I will check again. You see, I check every single region. The graph goes down, negative. So we know where there's negative or where your straight line points downwards, the graph is decreasing. Where it points upward, the graph is increasing. So all we have to do now is to check, okay, these are our critical points, our points of interest. So surely from this point to the left, the graph is decreasing. Also from this point to the right, the graph is decreasing. But between these 2 points in this region that I will highlight in blue, the graph is increasing. So if we are to answer this nice, easy, straightforward, this is what we will say. For which values of x? Well, surely the graph is increasing when x values are between 1 and 3. But the graph is decreasing if x values are less than 1 or equal to, but also if they are bigger than or equal to 3. the graph is also increasing. Those who like interval notation, you could write this and say x is an element of what? 1, 2, 3. Here you could say x is an element of what? From minus infinity to 1, union 3 up to infinity, up to you. These literally mean one and the same thing. So this is, for me, this is the power of using the straight line, the gradient. It works out so well. You don't actually have to worry and do some substitution. By just doing a basic, simple straight line test, you can tell where the graph is increasing and when the graph is decreasing. What I'm going to do is to pause now and actually give you a problem to try out, because I do not want to run and only to find that we are actually not on the same wavelength here. Yeah, so here's your simple test question. So I want you to try this, and I will pause here and allow you to do this. I'll give you about 5 to 10 minutes, which is a lot of time, but because it's the first time, I'll really just allow you to do this. So the question says, find and classify the stationary points of f of x. Maybe let me not use f of x. We used f of x a lot. Let me use a different notation and see what you guys will come up with. Of y is equal to x cubed plus 3x squared plus 3x plus 5. Now, what does that mean? It means you will tell me whether that stationary point is a local maximum or a local minimum. That's what we mean by classify. Describe it for me. Is it a local minimum or a local maximum? So that will be part A. Part B, once you have done that, I would want you to draw a rough sketch representing Y, representing the above, basically. Now, when you have done that, I would then want you to do the following for me. I would want you to then determine the values or write down values of x for which y is increasing, that is number one, or and decreasing, or decreasing. Okay, give me those. Give me those. I would want you to do that. If you can do that, then you have understood what we have done today. Okay, you have completely really understood today's business, which is good, because then it is a good foundation for sketching those cubic graphs. All right, go ahead. I'm gonna stop talking here and I'm gonna set my timer. I'll give you about 6 to 7 minutes to complete this. So, first of all, you got to find the derivative, and that is where now again, I'm just checking. I deliberately made it y, so you're not going to go f of prime here. Your derivative here, you have to use the notation dy dx. If you have not used that, I can guarantee you 1 mark gone. So then you have 3x squared plus a 6x plus a 3. Now, what should we do? We should set the derivative to 0, and I'm solving a quadratic here. Just bad math here that I'm writing, but I just need to get to the answer now. X squared, 2x, 1, So, this one is an interesting one, guys. Oh man, I feel for you guys on this one. So we have x plus 1 into x plus 1 equals to 0. So which means x is a -1 is the only stationary point that we have. Now, which means, Shem, I did really do a stretch here. I should have checked the question first before asking you to do this. I did a stretch here because you're gonna have something like that, and then this thing will not actually decrease a bit. Yeah, because you only have one stationary point, which is possibly a stationary point of inflection. Um, yeah, so that's the issue. That is the challenge here. So I think you are excused from question B and C because I have not covered that yet. What I will actually do so that you are able to answer it, I think I will talk about the second derivative test. I thought I would do that in the next lesson, but since we have now been led to this part, I think it is only fair that we talk about the second derivative test so that you are able to do that particular question. All right, now remember f prime of x. If I give you f of x, given f of x, just remember, given f of x, then you have to know that f prime of x is called the first. It's important to note this word first. It is called the first derivative, also known as what? The gradient function, the gradient function. And if you want the actual gradient at a certain point, you will then substitute that x value into the gradient function, which then means f double prime is called the second derivative. That's what it is called. Okay. Now, if I give you y, I want to show you how it works with other notations. If I give you y, then dy dx is your first derivative, which means that will be your second derivative. So it's quite important to actually note how these different notations are used right through the board. So please just be aware of that. I think I left an X squared here. That's how they represent the second derivative in terms of dy dx notation. Okay. Then what are we going to do now? We're going to learn how to calculate or find the second derivative. And then after that, we will actually see its application when it comes to sketching functions. So let's suppose we've got f of x is equal to x cubed minus 5x squared plus 3x. Then obviously the first derivative will be 3x squared minus 10x plus 3. Now, the second derivative basically means you take the first derivative and derive it. So that's 6x minus 10. Now, please pay attention. Note, this is a cubic. The first derivative of the cubic is a quadratic. And the second derivative of the cubic is a linear function, which means here the picture will look like that. Here the picture will look like this. And here the picture will look like that, just a straight line. It's actually interesting to note how the cubic function can be changed into a quadratic function and the quadratic into a linear. This relationship will be explored later on. You will see how important it is to note and know how these three are linked. Okay. Anyways, this is our second derivative. Now, why does it matter? Well, you remember I spoke about your local minimum, local maximum type of stuff. We can actually use the second derivative to help us determine whether a local maximum or a local minimum exists at a certain point. So let's take this cubic function. I want to show you that. So obviously, here is some concavity and there is some concavity there. Now, what is interesting is if I know my second derivative and I substitute a point called A here, and I notice that this is, in fact, this is what will happen in a case of concave down. In a case of concave down, you will notice that then the x value that you substitute into the expression of the second derivative is negative. Once that happens, or once that is the case, then you know you have a concave down. But then you will have a concave up situation if the x value that you are substituting, let's call it a b, produces a positive answer. So obviously you are substituting into the second derivative. All right. Once this happens, then you know you are concave up. Think of it of the parabola. When A is yeah, well, it's a very silly one, but you know when A is negative, it's a sad face, which would mean concave down. And when A is positive, it's a happy face, which means concave up. That's if you just want to memorize it and you don't want to do a lot of work for yourself. Now, there is an interesting point that we must also be aware of. This is a point that actually separates concavity. In other words, this is a point where the graph changes from being concave up, or concave down to being concave up. This special point or point of interest is known as the point of inflection. This is known as the point of inflection. Now, it is very easy to find the point of inflection. To find the point of inflection, you simply set the second derivative to 0. So in this case, if we go 6x minus 10 equals to 0, then we'll have 6x equals to 10, which means x is 10 over 6, which is something like a 5 over 3. So that will be the x coordinate of the point of inflection. If you want to know the y coordinate of the point of inflection, you're going to substitute back into the original expression, that is f of x. Okay. It is also important, though, don't get trapped in this, okay? It is important to note that just because I've got an x value by setting the second derivative equals to 0, it does not necessarily mean that will always be the point of inflection. It's never a guarantee. So it's always important then that you do the concavity test to check whether that point is actually a point of inflection. And what will you do? So to do that, well, let's say this is our point. Let's call it C. You will substitute any value that is less than C to see what you get in that second derivative, and any value after C to see what you get. Obviously, we want to have a change in signs. If we get a positive, then we must have a negative. Then we know it's a point of inflection because concavity changes. Or we get a negative, then a positive. Then we know there's change in concavity there. But that is a simple check to know that there is concavity change. There has to be a situation where it's either the graph is concave down before the point of inflection and then concave up after that, or concave up before the point of inflection and then concave down right after the point of inflection. That is extremely important to note, okay? So whenever you want point of inflection, what are you going to do? You're going to set the second derivative is equal to 0. And that will be our discussion in the next lesson. So what I will do, I think it is only appropriate to leave you with homework, with something to try out, and you will then submit that via the WhatsApp thing, via the WhatsApp. So you're more than welcome to do that. So I'm going to close it off by doing that. And I think for me to do that properly, I will have to bring out a question from one of the past papers so that you actually see how this is asked at exam level. So where's my paper one booklet? And I get that. So we're going to put that together and then you're all going to try it. So we're going to take your question from the past papers and then we try it out. The calculus section. You should all have access to this. I have posted it in the group chat. So you're going to go under the calculus section. Let me just bring this up. So we're going to do this. This is under the calculus section. Yes. These are the stuff you should be able to do by now. This is just generic stuff. I want, see here you are being told about local maximum, local minimum. This is a nice question, actually. Let's see. Let's try and find a fair question for you guys. Okay, so this is what you're gonna do. This is what you're gonna do. You see where you have been asked to find the turning points. That's what you're gonna do. That's all I need you to do. I just need you to calculate the turning points. Calculate the turning points. That's all. So you go over this section where you've got, I want to see, where it's under calculus, but now where you've got fun graphs like this. Okay. I think you can also do this one, but that's if you know the values of M. Yeah, but let's see, you could do this one. They've already told you that M is 18 and N is negative 27. So try and do this one as well. I think you could also try this one. I think this is also a very good question. It's very theoretical where they ask you to explain something. So this will also be a good try. This question 9, very excellent question. And I would also suggest that you try this one here. You should be able to do that because that's just solving for X. We have done that. You can do your long division, whichever way you're going to get there. You should be able to do that. That's what we just did today. And then you should be able to do this one. Yeah, so you may skip this one because we're only going to sketch next week or in the next lesson, and don't stress about this one. But if you can do these 3 questions, and I think this is the one that I'm actually going to put up there, this free state one. If you can do these, I'll be pretty much happy and impressed actually. Start with these ones. If you can do this, guys, I promise you, you're going places. So yeah, go ahead, try this, send me your solutions. I'll engage with you. And yeah, that will conclude it for today. We meet again on Sunday. Cheers.